So, welcome to our ongoing now EOL seminar series, and we shifted the time a bit, but we're happy to be able to do this, to have Sandra Yuter here. She gave us a resume, and I'll try to flip through it. Got her bachelor's degree. Should I give years or just?
No, I don't give years.
Okay.
A while ago.
From Brown University, and was working in private industry for a while, and then in 1988 joined what was then ATD, and she was working as a software engineer, and apparently got so excited about working in research that she decided to go back and suffer more education. I don't know exactly, but it looks like they immediately sent you you immediately then went into the field for CAPE and Toga Core.
Yeah.
That was as a student?
Yeah, CAPE and Toga Core was as a student, yeah.
Yeah, and which of course many of you guys know. Did get her PhD from then the University of Washington, stayed on getting to be a research associate professor there, and in 2005 went to North Carolina State University, where she's now a professor in the Department of Marine, Earth, and Atmospheric Sciences. She's, of course, been on lots of NASA teams, DOE teams and panels, and worked on DOE ARM, various capacities, AMS committees, of course. She's now the editor of JAM, Journal of Applied Meteorology and Climate, and is also on our OFAP panel. So I think with that, I'll let Sandra start. Thank you.
Okay, well, thank you for inviting me. So today I'm going to talk about low marine clouds, drizzle. Okay. This was to kind of give you as I said, sort of just kind of get you in the mood. So I want to just acknowledge my co-authors. The names in yellow are my students. I had 3 master's students and 1 PhD student finish last year, so they've all contributed to this talk. And put this away. Okay, put that away. And my other collaborators, Sandra Yuter and David Meacham. So I'm going to be talking today about the cloud lifetime effect, which is one of the big aerosol indirect effects. So just kind of a review. When we have correlation, it doesn't mean we necessarily have causation. This is one of my favorite plots. I'm showing this. Okay. So if we do have correlation, what does it mean? So it could be A causes B, B causes A. They could be caused by a third factor. So it's a coincidence. But in order to have causation, you have to prove it. And you can do that with a controlled experiment or a testable hypothesis. And one of the issues in sort of mistaking correlation for causation is this neglect of common cause. When you say one thing causes another, when in fact both they're caused by something else. So an example of this is the number of supermarkets, the number of hardware stores. Those 2 numbers in a region tend to be highly correlated, but it's not like supermarkets create hardware stores. They're both related to population. All right, and the other thing I want to talk about is a problem that we as humans all have, even though we like to think of ourselves as very rational and very objective. To some degree, we all have a confirmation bias, where we tend to weigh information that confirms our beliefs more heavily than information that disagrees with that. And so sometimes this happens where 2 people look at the same data and see different things depending on their preconceptions. So I just want to kind of get that, sort of remind you of that. Everybody knows about it, and we all have it. All right, so what I'm going to be talking today is what I'm basically going to make a case that there's been a neglect of a common cause, and that common cause is the sun. All right, so the cloud lifetime effect is basically described as related to what happens when you have a small amount of aerosol. So at the top, you have sort of a low amount of aerosol in cloud. When you have a lower amount of aerosol, you have an albedo effect. You have fewer larger drops. And the lifetime effect part of this in regions of low aerosol is that those larger drops, those clouds with larger drops, are more likely to rain. As a consequence of that raining, the cloud, decreases. All right, and this is compared to in regions with more aerosol, where the drops are more numerous and smaller, the cloud is less likely to rain, the cloud is more likely to persist. So that's the basic idea. So a good place to test the cloud lifetime effect is in open ocean, far away from land, where the aerosol concentrations are low. And also pick a place where the cloud system is pretty simple. And one of those places is the marine stratocumulus regions, where the clouds are all liquid phase. All right, so in terms of the IPCC report, the cloud lifetime effect, basically it's one of those things where our scientific understanding is very low. So it's sort of an area ripe for further investigation. All right, so another aspect related to the cloud lifetime effect is this idea of the simple rainout. And this is actually in the original paper that Bruce Albrecht wrote. But the basic idea is the time it takes for the cloud to rain out is related to the liquid water path, how much liquid water is in the cloud, and the rain rate. For values in the stratocumulus region, if for a typical sort of liquid water path with drizzling cell, about 300 grams per meter squared, and a 1 millimeter per hour rain rate, you get a rain out of about 20 minutes. So these cells would form, and the stronger ones would rain out in about 20 minutes. Of course, if your liquid water path is sufficiently low, you don't get any rain at all, the cloud will persist. And ones greater than about 200 grams per meter squared usually do rain, and that's based on a lot of empirical data we've collected. All right, so where are these low clouds? There's 3 primary regions in the Northeast Pacific, the Southeast Pacific, and the Southeast Atlantic. I'm going to be particularly focusing on the Southeast Pacific. And you can see that, the cover, this is the annual mean cloud coverage. Those higher values are up in the 50s and 60% of the time. All right, so just to give you an idea of scale, we tend to think of hurricanes as big and important, and they are. This is actually Hurricane Irene. This is the stratocumulus region that we're looking at. So from a global perspective, it's very large. It also has a very important role in terms of the global radiation budget. Whether or not we represent these clouds correctly, is important in terms of our climate modeling. The region has these low clouds because it's an area of large-scale subsidence. So we have the Hadley circulation, the upward motion at the equator. Then we have subsidence, and we have an inversion. And it's basically what we have is a boundary layer with the clouds underneath that inversion. And we also have upwelling on those coasts of the continents, and we have colder water as well. All right, so what do these cloud decks look like? They actually have some really interesting details. You can see it's not just a flat, homogeneous structure. We actually have regions that have closed cells and also regions that have open cells. And from the perspective of albedo, it's pretty obvious that the regions with the closed cells, right, are going to have a higher albedo, more reflect shortwave than the regions with the open cells. So it's important to understand these types of transitions because that affects the radiative balance. All right, so I know Jim really likes nowcasting, and every time I talk about drizzle, he just sighs at me. But I try to come up with some reasons why.
He told me to come.
That's why I told you to come. Why he might care about this. Okay, so why he might care, right? The sun is not changing with anthropogenic climate change. These stratocumulus cloud regions are highly reflective to solar radiation, but they have only a small perturbation in the long wave because they're so low, their temperatures are not that different from the underlying ocean. So if you just change the cloud coverage by 7%, you can offset, because these have a net cooling effect, you can offset the warming by CO2. So another way to think about it is a small error in our estimates will lead to meaningful errors in the temperature trends. So it's, again, important to get these clouds right. And so basically, if we can understand and improve predictions of these types of clouds, we'll get a better idea of have more accurate long-term predictions. All right, so I'm going to define. You're convinced, really? I didn't think you would be. Now stay. Okay. All right. So I'm just going to define cloud fraction. Cloud fraction is one of those terms that has a very imprecise definition. It's also scale dependent, but for my purposes, I'm going to use two primary definitions. One is how often cloud is above a point. So this is a cloud fraction definition at time. The other is for a single point, for a single instance in time, what percentage of an area has a particular cloud fraction. So this is just illustrated here. All right, so if we look at the Southeast Pacific, what we see is, and I've contrasted the season with the most cloud and the season with the least cloud. I think I'm supposed to use this. Okay, so overnight, the cloud fractions are really high. You notice it's basically, almost pegged near 100%, and they're so it's a highly skewed distribution. And then as the dawn comes up, the cloud fraction decreases, and then the cloud fraction starts increasing again in the afternoon, and then it's very high overnight. All right, and then this is basically the season with the least cloud. Notice that it's not as close up to 100%. We sort of have more variability, but we see the same general trend. This is the same information, only looking in terms of the rate of change. So we're seeing overnight small rates of change, during the day decreases, and then starting about 3 o'clock, actually the rate of decrease is changing, and then we're starting to increase and fill in that cloud overnight. All right, so this is sort of like the background. Those changes in cloudiness, I'm sure won't surprise you at all, are highly correlated with the incoming solar flux. Right, so the minimum cloud, where we have the maximum solar flux, and then we're starting to fill things back in when that sort of rate of change, the rate of change of the solar flux is so we're decreasing the amount. All right, so what are the processes that modify cloud fraction? So it's actually a bit different than deep convection, because these clouds are actually driven primarily by negative buoyancy. So overnight, she says, okay, overnight you have cooling at cloud top, long wave cooling. That creates negatively buoyant parcels. Those parcels then sink, and that creates essentially a mixing of the boundary layer, which then brings moisture up to the cloud deck and helps fill in the cloud. Okay, so instead of being positively buoyant parcels at the surface, these are negatively buoyant parcels at the top of the boundary layer. All right, you can see that here. So we contrast that with during the day, and in this case, where's my little mouse here? Okay, so the sun comes up. Now I'm going to be offsetting that long wave cooling with short wave heating. My parcels are not as negatively buoyant. They will sink, but maybe not all the way to the surface. And what we get is a kind of what's sometimes referred to as decoupled boundary layer, where you have a surface mixed layer and turbulent mixing of the moisture from the ocean, but the cloud layer is to some degree cut off from that source of moisture, and because of cloud top entrainment, we essentially erode away the cloud during the day. All right, so how well do climate models represent these kinds of clouds? Not very well. They struggle. Okay, this shows the diurnal cycle. So the black line is the observations. These are all the models. Models struggle with both the amplitude and phase of the diurnal cycle in these clouds.
What kind of models you're referring to?
Sorry, these are a bunch of different. There's some climate models, and then there's some regional models. So here's some climate models, and then I think
there's
some.
No LES here, am I right?
No, there's no LES. I'm not. Yes, the LES can represent them, but in terms of the climate models, yeah, and those examples I showed were LESs. Yeah, the climate models have a lot of difficulty representing the amplitude and the phase. The climate models have a lot of difficulty representing the height of the cloud deck, essentially the height of the boundary layer. In this case, the observations are these X's. And the models also have a lot of difficulty representing the thickness of the cloud. And so all these are sort of basic fundamental properties of the cloud, which if you get wrong, it's not surprising that you then get cloud fraction wrong as well. And if you get cloud fraction wrong, then you're going to get the radiative balance wrong. Okay, so people are aware of this. This is kind of one of those big problems with climate models that people talk a lot about, and that there's work going on. Another big problem is the double ITCZ problem. But one of the things that people have been focusing on is the role of precipitation, all right, and this cloud lifetime effect. So how would it change precipitation? Or sorry, how would it change cloud cover? So basically, strong precipitation has been implicated in regional cloud cover change. The idea is that, you know, in that little cartoon I showed you, we deplete cloud water. We're going to have cooling below cloud. Drizzle evaporates, creating a stable layer. That stable layer helps to decouple the subcloud layer from the surface. So that's a way of reducing the cloudiness. There's also some work being done about oscillating behavior of open cells, and I'm not actually going to talk about that today. That's some work that Graham Feingold and Chris Terai are doing. An important thing to note about this is that this reduced moisture transport occurs with precipitation, but it also does occur during the day as a consequence of the reduced negative buoyancy of the cloud top parcels. All right. So when my students started giving me the results, which were basically disagreeing with the cloud lifetime effect, I went back to the literature and said, okay, well, what was the evidence that precipitation is decreasing cloud fraction in these marine stratocumulus clouds? And I found an amazing coincidence. So you go back to the Wood paper, which has some examples. So this is time here on the bottom. I've annotated sunrise and sunset. This is the cloud radar on the ship looking up. So it's not looking very big, broad area. It's just over the ship. You got the cloud fraction here. So overnight, we've got some precipitation. The cloud fraction goes down. But then the big change in the cloud fraction coincidentally occurs after sunrise. Okay. Here's another paper, Stevens et al., using the DICOMS-2 data set. They were flying around in one of these pockets of open cells. The aircraft is flying around, seeing heavier precipitation in the region where the cloud is more broken. This is one of the key examples that have been used as evidence of the breakup of cloud by precipitation, but it coincidentally happened at dawn. Here's a paper I'm a co-author on, where we looked at the transition of clouds from closed to open. Here's the accompanying radar data that goes with it. You'll notice the radar cells, become a little more intense, a little more isolated, but it coincidentally happens at dawn. So here's another example. You notice there's a theme here. From Vocals, the C-130 flight. This is not the most clear example because there's some high cloud here, cirrus cloud blocking, but there's breakup of the cloud deck associated with precipitation. You can tell that it's occurring at dawn because Rob actually switches from using IR data to visible data. Okay, so when you go back in the literature, and I think this might be related to this confirmation bias problem, yeah, we do have evidence of heavier precipitation close with cloud breakup, but the examples in literature coincidentally happened at dawn. All right, so what's going on in these clouds? This shows 2 days worth. So in terms of the diurnal cycle, you know, we tend to get precipitation overnight. Sun rises, we get a little more precipitation, the cloud thins. So this is, and then I sort of indicated some IR data here on the bottom to sort of give you some context. So it's pretty normal for it to rain overnight, past dawn, and then sort of stops raining during the day, and then it starts up again in the evening. Also, these variations in cloud top height are also related to the triggering of drizzle, and we've written another paper about this. Okay, so there's clearly a strong diurnal cycle. Can we really say, can we isolate the evidence for the cloud lifetime effect? To do so, we would have to just look at night, right? Because if we're going to have sort of a covariation of cloud breakup and the sunrise, we can't really say that's because of precipitation. All right, so the Vocals experiment was meant to address some of these questions. We used a lot of different platforms. I'm going to focus on the data from the Ron Brown, which was further out in the deck because it doesn't need to go back in every few hours. Particularly the C-band radar, and then we also have soundings that we took from the ship as well. All right, so we're getting precipitation information 60 kilometers around the ship every 3 minutes, 24 hours a day, 7 days a week for the 31 days that we're out there. And we also have cloud fraction information from GOES data, both the IR and the visible. We're going to use the IR because we have that both during the day and the night. Okay, so just to remind you, this is what it looks like during the day. I showed you this before. All right, so we then take that radar data, and we're going to focus on precipitating, things that are precipitating cells, because we know, or at least the theory says, that the stronger the precipitation is, the more we're likely going to have that rainout process, the more likely we are to reduce the cloud fraction. All right, so we're going to take our reflectivity field. We're going to say a contiguous region of reflectivity is something we're going to call a blob or precipitating cell. And we're going to sort of look at how that varies, that co-varies with the cloud. So this is actually now the radar and the IR. And so the daylight hours are from 12 to 0 UTC. So let's go, let's get the day. I think we're up there. So now we're day, 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 night. So yes, there's definitely a covariation. And if you look carefully, I can come up with an anecdotal example of stronger precipitation is close associated with cloud breakup, stronger precipitation is close associated with clouds remaining the same, weaker precipitation or no precipitation associated with cloud breakup, weaker precipitation associated with clouds staying the same. So from an anecdotal standpoint, yeah, but that's not very strong evidence. So let's look at the whole data set. All right, so we take our field, we apply some thresholds, we also get rid of the smaller blobs, and then we actually have to apply an area filter because I've got the cone of silence and sort of the edges of the domain. And the reason why I'm going to get rid of them is because we're going to be tracking. So I'm actually following a method that Mike Dixon and Gary Wiener did quite a while ago, but still the gold standard. And we basically track all those cells. And so by tracking them, one, we can make sure they're actually cells and that they're not some kind of clutter, but also now we can get characteristics of the cells along the track. So the types of information that we can get, we can get...
Sorry, what's your altitude difference when you're looking up to your
so basically what I do is, so the cloud deck is only like 1 kilometer to half a kilometer thick. And so I think this is basically the maximum reflectivity in the cloud deck that we're using. So so basically what I've done is I've constructed a reflectivity field so I have a number of tilts that's basically using the maximum reflectivity in the deck as the indicator where the cell is. There's some variations in the height of the cloud deck associated with longitude, and so this sort of helps compensate for that. Okay, so here's all the tracks. They basically follow the ship. We have more tracks where the ship hung around when it was doing buoy maintenance or other reasons. So we ended up with almost 10,000 tracks, longer than 15 minutes. Sorry, yeah. And of those, we have about half that originate inside the radar domain and dissipate inside the radar domain, so we're reasonably confident we got the whole life cycle, right? And we're not just catching a piece of it. About a third are longer than 30 minutes, and a very small percentage are larger than 90 minutes. Think back to that rainout number, about 20 minutes. So we do have a subset of tracks, subset of cells that are exhibiting much longer much longer lifetimes than can be accounted for by that. And I think this is an indication there may be some recycling and replenishment of the liquid water. All right, so what does this track information look like? At the top, I've got some snapshots of the track of the cell at different locations. And then we can also look at, for example, things like the area or the max intensity. We can also just actually look at the distribution of intensities within the cell at any given time. So this is sort of a simple hump, right? It increases in intensity relatively quickly and then sort of decreases more slowly. We do sometimes get more complicated patterns where actually it'll pulse. Okay, so I can take all that track information, get a bunch of different statistics. So now I'm sort of getting at the behaviors along the track. All right, and so now I can, get, the distributions of peak intensity, median intensity, area, duration, etc. And I can also combine that information and do, joint frequency distributions. And what this one shows, so this is intensity versus duration. is that the tendency is that for the stronger cells, the tendency is that they tend to live longer. Okay, so let's get back to the sun, though. All right, so what's been observed to vary with the diurnal cycle in these regions? Obviously, long-wave and short-wave fluxes, cloud fraction, this subcloud turbulent moisture transport, things like cloud top height, cloud base type, cloud depth, liquid water path, number of drizzle cells, drizzle area, and the areal average rain rate. All these have diurnal variations. Things that are not observed to vary with the diurnal cycle, the aerosol concentration. This is not an area with high chlorophyll productivity. Near surface wind speed, conditional rain rates, and the proximity of drizzle cells also does not vary diurnally. All right, so back to this, just to remind you. So we had this diurnal cycle of cloudiness, where it's very overcast overnight. We tend to have breakup during the day. We can use that ship radar to now give us the diurnal cycle of the drizzle area and the number of drizzle cells. And we see that both these peak around 2 or 3 a.m. These are two different parts of the ocean, east and west of 80 degrees west. But the peak, and we'll focus, which is where the more drizzle is, we'll focus on the western part. Yeah, it's peaking about 2 to 3 a.m. So if there's a strong cloud lifetime effect, we would expect to see it associated with the time period where we have the strongest amount of drizzle and the heaviest amount of drizzle. Okay, but what do we see? So this is basically combining the data from those two other plots. So for the ship domain, we figured out what the cloud fraction was, and then we also looked at the area average rain rate. Right? So the top plot is basically just the change in cloud fraction with time, and we've color-coded these dots. So this is that 3 a.m. time. So basically, given starting at 3 a.m., what happens to the cloud fraction 1 hour later? What happens to the cloud fraction 3 hours later? And there's not a huge signal in here, I would argue, that, you know, at that time when the precipitation peaks, there's a big change in cloud fraction. If we sort of then sort these dots by area precipitation rate, we also don't see a big signal, right? There's changes, positive changes in cloud fraction, negative changes in cloud fraction. We do have decreases in cloud fraction associated with little or no precipitation, both at the 3 hour period and the 1 hour period. Okay, so we're not really seeing clear evidence of this cloud lifetime effect. Okay, so we would expect, and in fact, if you count the dots for the ship data set, so if we say you've got to have more cloud fraction that's a decrease more than 5%, only 4 out of 289, so about 1% of the 1 hour samples, only 3% of the 3 hour samples actually showed any decrease, if you include sort of even both the low and the whole evening period. So another message of this is not only are we really not seeing an evidence of the cloud lifetime effect, we're also really not seeing strong evidence of cloud fraction decreasing very often overnight. So I'm not saying it doesn't happen. I'm saying it doesn't happen very often. Most of the cloud fraction decreasing we're seeing are during the day, when they can very easily be explained by the sun. All right, so let's kind of look at this a little further. We're going to define some cloud condition categories following the standard definitions: scattered, broken, and overcast. And then we'll have another fourth one, the transition when the cloud cover changes between these. All right, so this is just the distribution of cell peak intensities by cloud cover. This is not normalized. I want to show you this first, just to show you that most of the time it's overcast. And in particular, overnight, it's overcast a lot. There are some other conditions that occur, but much less frequently. But let's normalize this now so we can see it a little better. All right, so what can we say about the intensities and the distribution of those intensities? So one thing is that in terms of the median cell, it doesn't seem to really care if it's day or night or what the cloud condition is. It's pretty similar. There are differences in the shape of the distribution. In particular, the distributions tend to get more skewed in the broken and transition than they are in the overcast. And so we do get more frequent higher intensity cells in those conditions. And if you actually sort of look at the numbers, that's 25 dBz. Actually, this is the 85th percentile. Is actually significantly higher in the broken at night than it is in the overcast at night. The median values are similar. We look during the day. Again, difference between the transition, so we got the transition and broken. So the transition's got a much more skewed distribution and a higher 85th percentile. So we are seeing strong peak. We are seeing strong cells in broken conditions and transition conditions. We're seeing those strong cells both in the day and the night. But they're outliers in the distribution. All right, so now what I'm going to do is okay, we looked at the condition. What about the changing of the condition? So I'm going to simplify things to just overcast and broken being less than full. And so now I've got 4 possible events. Or I could start overcast, end overcast, start overcast, end broken, start broken, end overcast, etc. All right, so what I've got here is the cumulative frequency distribution. So what this means is 50% of the time, the average precip area at night for all 4 conditions is around 16 kilometers squared for this 120 kilometer domain, 120 kilometer diameter domain. All right? But the real message of this plot is actually the similarity of these curves. So these are the 4 conditions. And they're, sort of similar. You might say, well, aha, look, those red and blue lines, remains broken, becomes broken, are actually different. Well, turns out that part of the graph actually corresponds to occurring with less average precipitation area, which is counter to what we would expect if there was a strong lifetime effect. So at night, if you got a little more precipitation, you're actually more likely to become overcast or remain overcast than you are to break up. Let's contrast this with during the day. During the day, I do have 2 different groups of lines. So I've got remains broken and remains overcast. So the cloud condition persisting is associated with more precipitation. The changes are actually associated with less precipitation. So we interpret this as actually related to cloud thickness. You're more likely to have precipitation if your cloud is thicker. And if your cloud is thicker, your cloud is more likely to persist. And then if your cloud is more likely to change if it's thinner during the day. So actually this is counter to what we would expect with a cloud lifetime effect. All right, so I would say drizzle does not appear to be a primary driver for decreasing cloud fraction. But you might say to me, yes, your ship data is very nice, but you're only out there for 31 days. Perhaps it's not representative. If you're going to make an extraordinary claim that the cloud lifetime effect doesn't look like it's really working, what other evidence can you bring to bear? So I'd like to bring in some satellite evidence. All right, so first, I got this problem of detecting drizzle. So it's great when I've got a ship. Here's my ship data out here. But obviously, they're very expensive, and you don't get them very often. So can I detect drizzle in the satellite data? Well, the standard product is the MODIS liquid water path, which is very nice. So here's sort of, you can imagine this is sort of let's say this is our ground truth. It picks up the drizzle cells very nicely. It's very high spatial resolution. The only problem is this product's only available during the day, and if we're going to want to test that cloud lifetime effect, we need to look at night, where we don't have the other influence of the sun. Another standard product is the liquid water path. This uses a combination of emission channels in the passive microwave, some of them at lower frequencies, and you'll notice it's pretty blocky. The size of the pixels is relatively large. A lot of these drizzle cells are small. Because of the beam filling effect, we're going to miss a lot of them. So we could use it, but can we do any better? Well, we realized that the 89 gigahertz brightness temperature is at a smaller spatial resolution, and it was picking up the drizzle. Now, for those of you familiar with passive microwave, 89 gigahertz is typically thought of as a scattering channel, but if you don't have any ice clouds, if you don't have any ice, what you see is the emission. So we're seeing the emission from the liquid water path, and we can use this as a drizzle proxy and thus look at a much larger data set. All right, so basically, radar's too expensive. This only works during the day. That's too coarse, so let's see what we can do with that. So what we did is we developed a product that uses that 89 gigahertz. And it doesn't give us the magnitude of the liquid water path. We basically adjusted it so that basically we're saying if the liquid water path is greater than about that 200 grams per meter squared, then we're going to say drizzle is detected. And if we compare that, so this is our product up here. So yeah, the MODIS is nice, but as I said, only available during the day. This is what the AMSRE is giving us, mainly because of limitations of beam filling. So we get a bit more. It's not perfect, but we're getting a bit more than we would with this product. And we know a lot of the cells are small, so let's try to get as many of them as we can. All right. So what times do I have satellite overpasses? I'm relying on the AMSRE instrument, which is on the Aqua satellite, that has overpasses at about 1:30 in the morning and 1:30 in the afternoon. So actually not too bad in terms of trying to get at the period associated with, at night where we have sort of a lot of overcast, and then during the day where the cloud is very broken up. Okay, where do those times fit in related to my my diurnal cycle of precipitation from the ship? It's not perfect, but it's a little before that peak in the drizzle, and then it's pretty close to the minimum as well. So not too bad. All right, so I can now use this data set, and I've got 8 years of it. And I can look at 3 by 3 degree boxes, and I can say, okay, let's look at the conditional probability. Given an overpass, I can figure out how much drizzle area there is. I can figure out what the cloud fraction is. And then I can then look an hour later in the IR data and see what happened. So if there's a strong signal of the cloud lifetime effect, we would expect to see some trend such that as the drizzle area increased, we would be more likely to have a decrease in cloud fraction. Okay? And sort of as a control, I put on the bottom cloud top temperature, which is indirectly related to the boundary layer height, which is also related to the coupling. All right, so what does the data show? It's pretty flat. Okay? What this is showing is the vast majority of the time, independent of how much drizzle area there is, cloud fraction is really not changing very much. And you could say, well, but look, there's some negative cloud fractions there. And I would say, yes, that's true. And I'm not saying it never happens. But, yeah, we also get some negative cloud fractions with little or no cloud drizzle. And if I sort of compare this to this boundary layer height, they're not that different. I mean, there's some variations, but there's not a strong signal here. This should be a pretty robust test. We're at night. There's no sun. We're looking, about the time when the peak drizzle is occurring. Just don't see the evidence. All right, so what is controlling cloud fraction? Well, if we look at the diurnal cycle, one of the things we notice is that cloud fraction changes a lot, sort of on the edges of the cloud deck, where it's it's sort of lower to start with. So these are two boxes. So the pink box is on the edge, and the blue box is more to the middle, and you can see this very large diurnal variation in cloud fraction. And this is just the variation in cloud fraction as a function of longitude, which is related to the boundary layer depth. All right, so there's pretty large variations here. It's 20 to 30%. These are happening, pretty much nearly every day. So if we now do a conditional probability and say, okay, what's the importance of the starting cloud fraction? So here's different cloud fractions at dawn, between 95 and 100%, 75 to 95, etc. All right, and then this looks what happens to the cloud fraction later in the day. And we see that the cloud fraction at the end of the day is very strongly related to the cloud fraction at the beginning of the day. In fact, there's almost, and we're sort of working to see how well you can actually sort of, parameterize this, relatively well behaved here. So if you want to know what the cloud fraction is going to be at the end of the day, look at the cloud fraction at the beginning of the day. What does this point to? This points to that it's the sun these positive feedbacks of the sun eroding cloud edges that are controlling the changes in cloud faction, not precipitation. This is a big effect. What about at night? Okay, so same thing, starting with very high cloud fraction. If you're overcast at sunset, you're very likely to stay overcast the whole day. And actually now, sorry, I forgot to point out, we're actually now looking at all three stratocumulus regions: Northeast Pacific, Southeast Atlantic. Okay, so it's repeatable. All right. If the cloud fraction, notice that the cloud fraction tends to increase, sort of independent of where it starts. And not quite at the same rate. So if it's actually going to fill in faster, a bit faster than if it, started already pretty high. Another thing to notice is you're going to say, well, okay, again, how often do we start with a high cloud fraction and end with a low cloud fraction? Yes, there's some points in here, but not very many. Very little, It happens. They're not very often. All right, so let's see, can we quantify that? Well, we again took our little boxes and then did time series of those boxes and looked at the cloud fraction. So this is an example, actually, of these pockets of open cells breaking up in here. And you can actually see the cloud fraction change. So we now have sort of a set of all these time series of cloud fractions changes overnight. And we can look at all 8 years of data. And sometimes we have a breakup of the cloud. And sometimes we just have more of a clearing that's more related to advection. We can combine all that information together and get an idea about how often is cloud breakup occurring overnight. So, not very often. So with 9 years of data, if we set a criteria and say the cloud fraction had to be at least 90% in this 3x3 box at some point overnight, less than 1 in 50 had a cloud fraction lower than 60% at sunrise. So that's 2%. Okay? So this translates into one POC-like transition in a 3x3 box about every third night in the Southeast Pacific. Okay? How does this number compare with different numbers? So Rob Wood actually did this by hand for 2 months of data. He found 23 POCs formed, only 16 at night. It's about a POC every 2.5 days. He was looking in the peak season, the peak cloudiness, peak drizzle season. We looked at the whole year for multiple years. So it's not happening a lot. All right, so to conclude, if I want anecdotal examples, I can pretty much find them for almost anything. So saying, this is in my terms of my community, we have to move past anecdotal examples. At night, what we see is overcast conditions with and without precip usually do not break up. But we sometimes see cloud breakup. It can occur with precipitation. It can also occur without precipitation. During the day, clouds with larger precip areas tend to maintain their existing cloud fraction because they're likely thicker clouds. Clouds that change cloud fraction are associated with thinner clouds. Some drizzle cells live quite a long time. Didn't really talk about this too much. Then can be accounted for by rainout. More intense cells tend to have larger areas and longer durations. There's also some indications that there's also proximity, which may help with this recycling. So the big conclusions are in the yellow. So for this spatial scale, about 100 to 300 kilometers, and the time scale of less than about 5 hours, what we see is that drizzle and cloud fraction co-vary. And that drizzle itself is neither necessary nor sufficient for reducing cloud fraction overnight. And that the impact is going to be small. So that 2% occurrence actually is 2% total. That includes with and without precip. So I can say confidently that the impact of drizzle reducing cloud fraction overnight is less than 2%. All right, so where are we back? So I can report back to the ITPC for marine stratocumulus, the magnitude of this effect is very small. Okay, and that for marine stratocumulus, this lifetime effect is occurring less than 2% of the time. So if we want to make models be more accurate, and this is this latest paper which is under review, there's different global models and then some regional models. This is the observations. I would argue that we really need to focus getting the diurnal cycle right, getting the cloud depth, the boundary layer depth right, getting the cloud thickness right, and not on the cloud lifetime effect. The cloud lifetime effect appears to be a minor player. And in fact, they did two intercomparisons, one prior to vocals and one after. They did a tremendous amount of work on the aerosol parameterizations, and they didn't really improve the representation of the diurnal cycle. So my suggestion is let's focus on the thing that's making the big contribution to the changes in the cloud fraction, and that's the sun. So I'll take questions.
Thanks, Sandra. I'm sure there's more questions.
So, if you go to your previous slide with this, this one, it actually has cumulus clouds, I would argue, not the stratocumulus in this picture. And then let me tell you why I bring the cumulus clouds, because I was arguing with people like Graham Feingold, for example, who actually spent some time looking at cumulus clouds life cycle. And I would say that's a really ridiculous way of thinking about it, because imagine two completely different situations, the cumulus clouds that lives forever and the cumulus clouds that lives 3 minutes. Mm-hmm. As long as your time average cloud fraction is the same, these two are basically irrelevant for the albedo effect, for example. In other words, if the scene is the same, or if it changes rapidly, so my point is that for cumulus, the cloud fraction is really irrelevant. I mean, cloud lifetime effect is really irrelevant. And I would argue that perhaps the same thinking can be brought into stratocumulus environment. In other words, you're looking at very small scales, and we know that drizzle is kind of epsilon squared. Cloud water is epsilon in terms of how much water vapor you have to work with. I like your talk. It's kind of nice overview, but I would argue, yes, Diurnal cycle is probably the most important thing that we need to worry about in climate model. And of course, climate people work on microphysics because they need to have knobs that they will turn to make their models work, and because they can do very little about the dynamics. Because this is small-scale dynamics, they turn into things that they can change, which is microphysics. And that's where all the confusion comes. And I think the cumulus cloud lifetime is actually a good example why, if you keep thinking about life cycle, this is kind of a dead-end street in my thinking. So it's really not a question, it's a comment.
Okay, so my data focused on marine stratocumulus. I mean, this is the cartoon from the literature, but if you look at the papers and the Albrecht paper and the other papers, they basically are saying it occurs for both trade cumulus and also for marine stratocumulus.
I really enjoy your talk, and I totally agree with you. The sun is more important than drizzle stuff. For cloud fraction. Now, using your data set, is there any way to find out, like a surface buoyancy flux diurnal cycle, how much is due to the solar absorption inside the cloud, and how much is due to increasing of surface flux, surface heating? Is there any way using your data set?
Not from the ship data.
But I thought you have observation of surface heat flux.
We do have surface flux observations from the ship, but the problem is we don't have the internal cloud shortwave heating.
All right. In order to put this effect into climate model, you need to know which one is absorption inside cloud, solar absorption that burn the cloud, or coming from below.
Well, I think we have a paper that's actually out in JAZ, which looks at the diurnal cycle, and one of the things that we have evidence of is that you can see these stable layers form during the day, such that you essentially have, a stability barrier between the low-level moisture flux at the surface and the cloud. So you can actually see that the cloud is cut off from the reservoir of moisture at the ocean surface. So I guess indirectly that would argue that what's eroding the cloud is the shortwave flux. Well, it's sort of a combination of the shortwave flux and the lack of water vapor coming from the surface.
Well, because it's unlikely that the sea surface temperature will change.
No, the sea surface temperature pretty much doesn't
So
change.
probably
But as I said,
more
from the
absorption.
sounding data, we can actually see these, stable layers in the middle of the boundary layer, and we can see that, and we can see with the LiDAR evidence that we essentially have, as some of the earlier cartoon shows, we have a surface mix layer. So during the day, you have, entrainment at cloud top, you have solar radiative forcing, and then you've cut the cloud off from the surface moisture. So those things are all coming into play. Unfortunately, from the ship, we don't have the internal cloud radiative
When you
fluxes.
talk about surface mix layer, you imply there is surface heating from below. I doubt it.
No, it's actually more just related to the wind flux. It's more related just to the wind. Go back here. Yeah, I mean the sea surface temperature doesn't change very much.
In order to get a change in the sea surface flux.
So fundamentally, there's not a big diurnal change in the sea surface flux because the wind speeds don't change very much diurnally. It's more an issue about whether that moisture from the surface makes it up to the cloud deck.
Yeah, you'd have to have a change in the air temperature
Right,
in order to get a change in the sea surface flux.
right.
So you're,
But I think previous work has showed that, as I said, there's not, the diurnal variation in the surface fluxes is small.
Yeah.
It's more an issue about whether the moisture makes it up to cloud level.
Well,
Okay.
there are no more questions. Thanks again, Sandra.
Okay.